So let's start with looking at this truss that's out there. I don't know what event is this for, do you know? Anyway, so this is actually pretty great because it's super simple, but also you can see how you gotta be able to tell what's in tension and what's in compression. So I'm gonna say, oops. So what's great is you can't push the cable, right? By definition, cables are always in tension because if you push it, it's just gonna do this. So just by glancing at it, you must be able to tell which member is in compression, which member is in tension. So is this in tension or compression? Right? How about this? Louder. How about this? Tension. How about that? Tension, right? And then this has to be compression, right? And that has to be compression. And that little guy should also be in compression. And it's skinnier, so there's gotta be less force than that big guy. So you're kind of halfway done with this analysis, but so I mean that's why this thing is kind of great, because just what it is tells you what it does. So if you open that extra analysis, that's basically what this is. Yeah.
What is this file?
Oh, okay. So it's I posted under last week's announcement. So week 2, right? I posted these 2 files called week 2 extra scissors truss stent. Anyway. So here's the diagram of that truss, pretty much exactly what it is, right? So now, yeah, sure, now just looking at this, we pretty much know that these guys must be in tension. These guys must be in compression. So let's kind of take a mental note of that. Now we have these nodes, and so to begin with, it's straightforward, but let's see. So let's just right, so again, I'm assuming the same kind of load as the previous homework, although it looks like, I mean, I don't know. I don't think there's 5,000 pounds on this thing, but let's just use the same number, right? And I'm representing 5,000 pound with 50 inches, so let's just say 50 inch equal 5,000 pound. So therefore the force scale is 1 inch equal 100, right? So that's our force scale, so let's keep in mind. So this is 50, and because it's symmetrical, these two 25 and 25, therefore the reactions are, you know, 2500. On each side. And I also labeled each of the nodes as shown, right? RS, I mean, it's arbitrary. So yeah, so this is where we begin with. So now I'm gonna start by labeling the zones, which I did here, but let me do that again. Yeah, so right? So outside of the truss, we have 1, 2, 3 forces, which is going to divide the entire world outside of the truss into 3 zones, which is between the left reaction and the applied force is zone A. On the right side, between this force and that force, is zone B. In between these two reactions, there is zone C. And inside of the truss, it's also straightforward. It's 1, 2, 3, 4. Yeah, so those are all the different zones, right? So now I am going to start a force diagram. Outside. So this one is that 5,000 pound force, so same length, right? So this one is between zone A and zone B, right? So I'm gonna name this force. This force is gonna be called AB. Therefore, the start point is A. And end point is B, because it's between A and B. The reaction should also be mapped, right? So this one, the reaction on the right is between B and C, and following that clockwise, it's going to be called BC. So that means it must start from point B. That's why I'm going to place it here. Let's kind of remove that. And it must end at point C. So I'm going to label the end point of the arrow as C. Next reaction on the left is between C and A, so the force is going to be called CA, and that's why it's going to start at point C. And if you if you drawn it correctly, then it must already end at point A. So this is kind of the beginning of the force diagram after mapping all of the vertical forces. So far so good? Yeah, okay, cool. So now what we were doing was we were going to focus on each of the point, right? So I'm going to zoom into point R first. And what you do is we're gonna look at each point with this clockwise notation. And before I do that, just to clarify, right, this zone is so this zone is still A, zone A, and the zone between this red and blue is zone 1. And zone between that bottom chord and the reaction is zone C, right? So just so that when we zoom in, we can see which zone is which. Is that good? Alright. So analyzing about point R on the left side. So we start by this, right? So we already have CA, which is right here. So that's already mapped. So we're kind of done with this. So now the next one is A1. So that means there's got to be force A1 starting from point A, ending at point 1. That is parallel to that top chord of that truss. So I'm gonna put this guy over here. And let me change the color to something neutral. I'm gonna show it as a dashed line. Maybe use the bigger. So anyway, so there's gonna be some force on this force diagram called A1, starting from point A, ending at point 1, that is parallel to this guy. If you compare this to this, these are parallel, so that's correct. But we can't really tell where point 1 would be at this point, so I'm just gonna call this one question mark. And it could be here, it could be anywhere on this line, right? So that's how much I can tell from that member on this point. So now we need to kind of move on to the next one, which is between 1 and C. So there is going to be a force called 1C, which starts from point 1, which we don't know where, ends at point C, which actually luckily we know where, and it's going to be parallel to this guy. So I'm going to copy this line to end at point C. I'm going to change the color to this dashed line, and that's the end point of this force. But there's going to be point 1 somewhere along this line, which is the start point. So now we have two separate information about pieces of information about point 1, which is we know point 1 is anywhere on this line and anywhere on this line. So the only choice now is intersection between those two. So I can do that by filleting without 0 radius, or you can extend or whatever, but you can get the intersection of these two lines, and that's gotta be point 1. So I'm gonna label that as point 1, and I'm gonna remove all of these question mark, and it turns out that we don't need that extension of that line. So that's basically how much information we can get out of this 1C, CA we already mapped it, right? So now we are going to move our focus to another point. The order doesn't really matter, you can go here or there, but I can start from point S. Again, I'm just going to clarify which zone each zone is, so just so that we know when we zoom in. That's zone 4, that's zone C. So let's focus, zoom in to point S. So now we know, okay, so let's start with this guy, C1. We know what C1 is, so that's mapped. Oh, by the way, I'm going to complete the force diagram first and then try to identify each of the forces, because that's kind of more simple. Anyway, so we are done with this guy, right? So let's look at 1, 3 next. So we know where point 1 is, and we know 1, 3 is gonna start from point 1 and ends at point 3, but we don't know where point 3 is on this force diagram yet. So basically what's gonna happen is I'm going to draw a line that's parallel to this member, 1, 3, right? And then point 3 is going to be somewhere on this line, but we don't know where, so I'm just gonna call it question mark. It could be on this side or that side, and that's all we can get from this member. Next one is 3, 4. This one's tricky. 3, 4 is gonna be parallel to this one. It's gonna start at point 3, which we don't even know where. So I mean, I'm putting it here, but really, like, who knows, right? It could be here or here. So actually that's like there's actually kind of too many unknowns, but that's all we can tell from this right now. Another thing is this guy is, so I guess we could call this point 4, but because we really don't know about this point, I'm just gonna call 4 question mark. This one that's between 4 and C, it's gonna start from point 4, ends at point C. So again, we have kind of a unreliable information, or I mean reliable but not enough. But what we know is 4C will end at point C, so it's going to intersect point C for sure, and then this kind of unknown point 4 is going to be on this line. But we can't really use this intersection point yet, because this whole thing is unreliable yet, right? Because it could be here, or it could be there, it could be anywhere. So these two are kind of somewhat not very reliable at this point. So anyway, that's all we can tell from this point right now, so we have to kind of move on to the next point. Yep.
Can you use the 4C and the 1C to find an intersection? Like those two?
1C. 1C is this. 4C is this.
No, not that one. Those two that are intersecting that we just found. That one and the
Right, so what's problematic with this guy is this guy, point 3 is not fixed yet, so this can be like anywhere. So I mean, I probably shouldn't even have drawn it, because this is still really not helpful, right? So yeah, so this is kind of way out there. Like we don't know. So basically we need to fix point 3 to be able to determine where point 4 is. So that's hopefully what we can achieve by going to the next point. So point 3, zone 3 and zone 1 and zone A, right? So let's focus on point U, and let's look at, I mean, this one we already know, 1A is here, this one is A2. Do we have that? We don't. So A2 is this guy. It's gonna start from point A and ends at point 2. So then we know. So right now there's gonna be a lot of unknowns, so it's gonna feel slightly frustrating, but just takes some patience. So point 2 must be on this line somewhere, but we can't really determine yet. So we have to move on to this point, this line, or that force. Okay, so this is between point 2 and point 3. Again, we don't know where point 2 is, we don't know point 3 is, but one thing we know is point 2 and point 3 must be able to, you must be able to connect point 3 and point 2 with a horizontal line somewhere. So you know, wherever point 2 and point 3 ends up being, there's gonna be some sort of a relationship like that, but the whole thing is unreliable still. And hopefully this would help us solidify point 3. So this force is between 3 and 1, so there is going to be a force that's parallel to this guy, right? Oh, okay, so that's still the same amount of information, right? So point 3 is somewhere here, So that didn't actually reveal much more than we knew before. So actually it really takes going to point Q. So let's go to point Q. So still this is zone A. Let me just label all these zones. This is zone B. So we only have zone A, B, and 2, right? So let's unlock. So 2A, we already used that information. AB, we already have. So there's going to be 2B, which is going to be parallel to this. Actually, B2, sorry. Starting from point B, which is here. Right? And because it's called B2, there must be a point 2 along this line somewhere. And from before, we also knew that the point 2 is on this line somewhere. So now we are finally able to locate point 2 because it's on this line and on this line too. So 2 is now fixed to here. And that actually helps because now, well, from memory we can tell that 2, 3 was this horizontal line and 3 is on this line. But let's just kind of go back. Let's just kind of rewind to that point. So this member was between 2 and 3. So that means there must be a force that's starting from point 2 and ending at point 3. Point 3 we don't know yet, but now we have located point 2. So now we should know that point 3 is on this line somewhere. And we also located from before that point 3 being on this line somewhere, right? So now we can locate point 3 to be intersection between those two lines. So that becomes point 3. So now, also rewinding from memory, because now we are able to locate point 3. We also know now that point 4 is on this line somewhere, but we haven't located yet. But also we also identified that point 4 will be on this line somewhere. So now we are actually able to determine that intersection point must be point 4. But I'm gonna keep going to next point to confirm that assumption. So in a way, we kind of, sometimes the order you choose to analyze your points, it, you know, like going to here had a lot more unknowns, but you know, it might have been easier to go from above. But either way you go, if you analyze all the points, you're able to determine all of them. So now let's look at point V. So now this is zone 2. Zone B is here. Zone 3 is here. And zone 4 is here. So now that's 2B. We already know that 2B is here, right? And so 2B is done. B4, using this, we know that there's got to be point 4 along this line that's starting from point B. We located point 4 actually, and this, so okay, so that's done. And if you look at that member, that's 4, 3. and where we located point 4, this line is also parallel to that member, and it ends at point 3, which we located before, so that actually works. So that kind of confirms our assumption. And then there are 3, 2, which is between these two. And I can actually kind of remove all these extra links. So that's more or less, I believe, is the diagram. But we can, the last point that we haven't analyzed yet is the point T. Point 4 and point C, no sorry, zone C is right there. So about point T, there's zone C here between these two. Oops. Zone C is between these two forces. Zone 4 is between these two, and zone B is between these two. So now this is BC, which is BC, right? So that's done. Then you get this one, which is C4, which connects C to 4, which is parallel to this one. So that seems correct. So that's good. And then you have 4B, which connects 4 and B. That is also parallel to that guy. So that seems correct. So the force diagram now looks intact, right? So now we can use these to determine the, let me kind of clean it up a little bit, or I can sort of remove all these extra dots. But now we should be able to determine the internal forces of each of these cores using, let me clean this up too. It's gotta be more.
I have a question.
Yeah.
So what do you mean by having that BC line?
Alright, so let's look at that. 2C, 2C, 2C. Okay. This?
Yeah.
Yeah.
Because it's not connected.
2C. Okay, so that's actually, so strictly speaking, actually there isn't this line on this force diagram, right? So there's only, what was that zone? 1, 2, so that's 2, sorry, right? I just did not trim it at the right point, right? So this is actually the correct diagram, because this stops at 2, right? So anyway, so that's more or less the force diagram, and we can use this now to determine the, determine the internal forces of each of these code. So let's look at that now. Let me also hide the identity of these points for visual clarity. Alright, so now let's see, actually I needed that. Anyway, so now let's use this force diagram to determine the internal force of each of these members. So let's say, what is this experiencing, right? So I really do need these points, even though it kind of gets in the way. But so let's look at the member RS, which is that bottom chord, right? So which is this guy right here. So this guy, if you look at point R, right, again using that clockwise motion, so if I look at point R, this one is called 1C. So about point R, the force that's in this member is 1C, which is to connect, start from point 1 and ending at point C. That's a really long force, but that's the internal force in this member at point R. What that means is this force or this vector should be inside this member and it's touching point R. So the only way you can place it that way is to bring this arrow here and dropping it on here, right? So that's the force, internal force in this member at point R, which is pulling the point R away. So that suggests its intention. And just to confirm that, looking at that same member at the other end, which is point S, if you look at point S, the force here is called C1, which is the opposite of this, right? Now it's gonna start from point C and ends at point A. Starts from point C and ends at point 1. So that's the force that's in this member at point S. And that kind of completes the forces in two ends in this member. So it's pulling two ends. So that's the that tells you that this member must be in tension. And as we've talked, I think in the first lecture, all the members in truss is called two-force member, which it's either in tension or compression, right? So if you will never have a situation where the internal force is like this, right? If it's like this, that means that bottom chord RS must be flying through space, right? So if it's doing that on one end, it should be doing the opposite on the other end. Anyway, this shows you, this indicates that this member is in tension. And the way to identify the magnitude of that tension is by getting the length of this arrow, which is 1/3, whatever that is. And because 1 inch represents 100-pound force, so if it's 103 point whatever inches, you have to multiply that by 100, and that's gonna be your force. So it's, let's just call it T. Yeah, sure. Pound force. So 10,300. That much. So that's how you determine the magnitude of that force. So I'm gonna, it's symmetrical, right? So I'm not gonna do the whole thing. I'm just gonna do the left side and then mirror it to the side. But now if you go to, now if you try to analyze the member RU, you're gonna have to again look at point R. So following this clockwise notation again, the force in this member at point R is gonna be called A1, right? So that is an arrow that connects, starts from point A, ends at point 1. And that's gonna be at point R inside the member RU. So the only way to put it there is like that, right? And if you go to the other end, point U, the same force is going to be called 1A. So it's going to be again the opposite arrow, which is starting from point 1, ending at point A. So that's the force at the other end, at point U, and it's pushing these two endpoints, right? So the internal force that this is experiencing is a compression. And again, you can get the lengths, and you have to do the calculation. So if you multiply that by, whoops, what was the lengths? Length is 111.803 times 100. So that's how much force is in here. And from here, you can, from this, the fact that two ends are pushing, you can tell that it's in compression by that much. So same thing. Let's look at that member US. Right. So if you look at S, point S, so let's look at US, and at point S, we know this one, but this one is going to be called 1,3, 1,3. So I'm going to connect point 1 and point 3. That's the force at point S. And if you go to point U, this is going to be called 3, 1. So that would be an arrow that connects 3 and 1. So therefore we know that is tension, and I'm gonna kind of skip that number thing because I'll have it in the answer. So we know that this is in tension. Let's look at this UV. UV at point U is gonna be called 2, 3. You're gonna connect point 2 and 3, ends at point 3. So that's where this thing is, which is actually pretty long. If you go to point V, it's 3, 2. So you're gonna connect point 3 to point 2, right? And these arrows are kind of like off proportion, so it might be confusing, but don't forget the fact that it's pushing towards two endpoints. So this is, again, is in compression. And we're gonna read the lengths later, or I'm just gonna skip that process. And let's look at UQ, which is, if you look at point U, this member is going to be called A2 because A is right here. So A2 would be a line that connects from A to 2, and that's what's acting at point U. So again, that must be in compression. And if you look at point Q, that's 2A. So if you connect 2 to A, that's the arrow again, and it's going to be pushing towards point Q. So that's also a compression. So if you do, and you know, the whole thing you can mirror it because it's symmetrical. It's not hard to assume that's the case. So if you read the whole thing, I'm gonna undo everything because in the beginning I had everything. So assuming all of that was done correctly, of course I crashed the thing, so I'm gonna reopen the, where is that extra? Right, so again, it's tension here at the bottom, tension here, compression at all of these, compression there, and you can see these tension, that tension significantly bigger, that tension small. You have these compression, and so if you calculate them, that's what you get. But yeah, anyway, but what's important is like that directly correlates with what you see here visually, right? Like compression, weaker compression, and then yeah.
Can you explain why that the small horizontal piece is in compression?
Okay, so if you look at U, right, focusing on this point, this member is called 2, 3, right, following that clockwise. So the force that's in there must be again, so this is 2, 3 at point U. So it's going from point 2 ending at point 3. So arrow would look like this, and that's the force that's acting at point U. So that horizontal member is pushing point U, so it must be in compression. It might seem slightly confusing because if you map the force at point U and point V, it's going to look like that, but it's just because the force scale was kind of too large to, if I'm using like much smaller force scale, it's going to look like this, right? So but what's important is to know that what the member is doing to that point U. In this case, we know it's pushing the point U, so it's, and also it's pushing point V, so that's how you can tell it's in compression. That makes sense? All right, so we've used quite a bit of time, which is, we have half an hour left. All right, so hopefully that was helpful. And now let's start with what we were supposed to start with today, which is this one, sample problem trusses beam. So let's see. Alright, forgot the name of the truss, but let's see. But let's open that file in the meantime. If you can open that file, it's gonna look slightly different, but you're gonna see two trusses like this. Let me actually open that too. So, but it should be week 3 sample problems truss as beam. That's the file that you're gonna get. In the meantime, typical common truss types. So those two are apparently called, one is called flat Pratt truss and the other one's called flat Howe truss. That's basically what I'm showing here, right? So 6 panels, and so if you watch the video, that's gonna, I mean, in that video I sound like I'm whispering because it was like 11:30 p.m. and I didn't want to be too loud, so but I think you can still hear me. But that's gonna explain this truss, so I think I'm gonna try to demonstrate the bottom one, so that covers everything. But what I really want to demonstrate here is that, like I said, I think in the first class, that if you analyze everything, you're gonna see this kind of pattern that top chord, all the top chords are gonna be in compression, and what's important is the compression at the top chord is maximum in the middle, and it gets smaller as you go to the side. Same thing with the tension at the bottom chord. The tension in the bottom chord is maximum in the center, as you can see. It's bigger here, and it keeps getting smaller. The compression's biggest in the middle, right? Small. Same thing with the other one, which is tension. So bottom chord is always in tension and gets smaller as you go to the side, and the compression at the top, the middle is the biggest. As you go to the side, it gets smaller. And that should kind of remind you of something, hopefully. Do you remember the, right, we all looked at that, so. Let's remember the beam with uniformly distributed load, right? What the moment diagram looks like is this one, right? And if you remember, well, if you don't remember, the easiest way to remember what the moment diagram should look like is take this loading pattern and imagine a cable with same exact loading pattern and what that cable does, right? So in this case, okay, so we have, let's see, I mean, we are basically talking about we're basically talking about something with uniformly distributed load. So if you imagine a cable with uniformly distributed load, which is basically a chain, right? Because each segment weighs the same. The chain is going to do that, right? It's just a catenary curve. And that's basically what the moment diagram is for this one, except if you want to show it in a conventional way, you might want to flip that, but moment diagram basically looks like that. And just to illustrate the point about the cable, if you think about the point load in the middle, right, what the moment diagram looks like for this one is if you imagine a cable with two ends supported with one weight in the middle, it's going to do this, right? If I have a weight here, and if two guys are holding the end, right? So, and that's exactly what the moment diagram is for this. So if you actually make that connection, if you look at the typical loading pattern for a beam, without doing all these counts, you should be able to kind of like pretty much guess what the moment diagram looks like. Because all you have to do is imagine a chain with these weights. That makes sense? Like if you have two, right, the chain would do something like that. If you flip that, that's the moment diagram, this one. But that's not really the topic for right now. But important thing is for you to remember a moment diagram of uniformly distributed beam looks like that. So what does that mean? What is a moment, right? The beam in bending, well, so beam under uniformly distributed load, it bends like this, right? I mean, it doesn't bend that much, and it's gonna experience a compression at the top and tension at the bottom. And it's that two combination of force, this and that causes this rotation, which is the moment. And that's what moment diagram is about. And what this is explaining is that the moment is maximum in the middle, of course, and then as you go to the side, it's going to decrease. So basically, this compression at the top and tension at the bottom, that's maximum in the middle, and it gets smaller and smaller as you go towards the side. So that actually nicely corresponds to the distribution of compression and tension in the top and bottom chord of the truss. So as a whole, it's basically working as if it's a beam, but it's a truss, right? So that makes sense? Okay. So, all right. So hopefully in 22 minutes, I can explain how to draw these diagrams. So it took me 30 minutes with a video, but all right. So because I already explained the top one in the video, which you should watch before the next class, I'm gonna be looking out for the view count. But yeah, so you can start the force diagram by first mapping all of these 5 forces, 1, 2, 3, 4, 5, right? So that's AB, and I already mapped all these zones. So A, B, C, D, E, F, G is the outside of the truss, and 1 through 12 is inside of the truss. Now, there are 5 forces that are equal to each other, connected. So A, B, B, C, C, D, E, F, and then 2 reactions going from F to G and G to A. So that's kind of it. And we're gonna look at point by point, right? So if I look at this one, the first one is GA, which is that second reaction here. So that's already mapped. Then the next one is A1. So first we know that there is going to be some sort of a vertical line starting from point A. Let me turn this into a dashed line too. And the point 1 would have to be somewhere along this vertical line, but we don't know where it is. So we're just gonna leave it at that. So point 1, we don't know where it is. And next one is right here, 1, 2. So there's gotta be a diagonal line parallel to this one, starting from point 1, which we don't even know where it is, and so we don't know point 2 either. So let's just leave it at that. So 2.2 would be somewhere, but it's really unreliable at this point. And then we also have 2G, right? 2G, which is horizontal, which is gonna be here. So 2 will be on here somewhere, and it's gonna be intersect with this diagonal line, but we haven't really located this diagonal line, so we can't really fix point 2 because this could be anywhere here. So that's kind of all we can tell from the first point. So we're gonna move to the next point here. And here the only thing we have is really A and 1, right? And there's a vertical force starting from A and ending at 1, which is this one. And this also actually suggests there's a horizontal member that's called A1 starting at point A, right? And it's horizontal, so going parallel to that member, and ending at point 1. So what we know is point 1 must be on this vertical line, but it must also be on this horizontal line. So which actually leads to the fact that the only possibility is the intersection between these two. So it actually forces us to conclude that point A is also point 1. And what that tells us is that A1, so if you connect point A and point 1 here to determine the force for these members, you end up with a point which you can see as a line with length 0. So what that means is the force in member A1, 1A or A1 is 0. So there's 0 force in this horizontal and this vertical in this case. Because yeah, I mean, it's not hard to imagine, right? Because if there's no applied load here, then these two are really not doing anything, and we can just actually cut it. And yeah, anyway, so that's where point 1 is, and that actually helps us to determine where this line is. So the point 2, so this line is actually now fixed, and point 2 is an intersection between these two, so we get point 2 from here. So we can delete this, we can delete this. Moving on to the next point. I mean, this is pretty cumbersome. So if you just, I mean, you can just watch for now, but you have to do it before next class. Otherwise, you're gonna forget. So I highly recommend you actually do it. So yeah, so let's look at this point, right? So the bottom chord, which is horizontal, is called G2, which we have already here, so that's taken care of. 2-3, which is gonna be a vertical member, and number 3 is gonna be on this line somewhere. And that's all we can tell now. And 3-4 will be starting from point 3, we don't even know where. And point 4 is going to be on here somewhere. But what's helpful is there is 4G, which is horizontal, which is starting from here. But it's not super helpful actually. So G2, 2-3 is vertical, 3-4 is this diagonal, and 4G is horizontal, starting from G. So still, this can be here or here or here or here. So actually we have to locate point 3. So we're gonna move on to the next point. Still, that's 2, that's 3, that's B, and that's A. So we have AB, we already have. B3 is going to help locate point 3. So B3 is a horizontal line starting from point B. And so that's going to tell us point 3 must be on this horizontal line somewhere. And we also knew point 3 was on this vertical line somewhere. So we are forced to conclude that the intersection is the point 3. And now that's going to help us locate this diagonal line, which had point 4, right? Somewhere along that diagonal line. Anyway, so AB, B3, and 3-2, now we have located. 2-1, we already located this, so we've used all the information that we can use from this point. So, oh, I'm gonna delete that. Yeah. So now, move to the next point. So the good thing is this is going to be videotaped and the other one I also videotaped. So what you should really do is watch the video, stop it, you do it, and then watch, stuff like that. Anyway, so there's a horizontal starting from the left side. There is a horizontal line called G4. So that's gonna tell us that 4 is on this horizontal line somewhere. So that's actually going to let us determine that the point 4 must be at the intersection of these two. So we can now locate point 4 and remove these question marks. Right? And actually we don't need that. We don't need that either. All right. So that was helpful. So so moving to the next one, there is 4-5, which is between 4, 5, there's a vertical one. And so 5 must be somewhere on this vertical line. Question mark again. And there's this diagonal one between 5 and 6. Again, right? So we don't know where 5 is, we don't know where 6 is, but 6 is gonna be on this diagonal somewhere. 6G. So there's gonna be 6 somewhere along this horizontal line, but that's kind of all we know. So that doesn't really help. So let's go to the top. Again, 4, 3, B, C, and 5. Alright, so for 3 we have here 3B, we've located it. BC, we've located it here. C5 is the horizontal line. That's the new one. So there's going to be a horizontal line starting from point C and point 5 to be on that line somewhere, which we knew also was going to be on this vertical line somewhere. So the only logical conclusion for point 5 would be the intersection between these points, these two lines, and that's actually going to help us determine where this diagonal line is. So that was 5, 4, no, that was C5, right? 5, 4 is this vertical that we already have. 4, 3 is the diagonal that we already have. So I have a feeling that in this case the top point at the top has more information, so I'm gonna move to that point. So now 5, 6, 7, B, C, and 8. And so this is CD, which we have. Actually, let's look at it from here. Okay, so there's a diagonal called 6, 5, which we knew, right? 5C is horizontal. CD is located. D8 is new one. Actually, I should have gone to the bottom, but anyway. So D8. There's a line starting from D, and 8 would be somewhere on this line. So that's what that tells us. And there's a diagonal line which is parallel to this guy called 8, 7, which is going to pass through point 8. And somewhere is gonna be 0.7, but that doesn't really help because right now they're not located. Let me change the color of the line that we don't know yet. So that's unknown, right? 8 and 7 is unknown. We have 7, 6, which is vertical. But again, we don't know where 6 is, we don't know where 7 is, but all we know is 6 to 7 must be a vertical line. So let's move down here. Now we have 6 and 7 and G. So now, looking at this one, there's got to be a horizontal one that's starting from G, ending at 6. So that really helps us locate this point 6 because it must be a horizontal line starting from G, and it's on this diagonal starting from point 5 too. So really the only possibility for point 6 is right there. and you can remove that extra portion of that line. Going to 6, 7, that's gonna be this vertical line, and 7 is gonna be somewhere on here. So then this guy must be somewhere out there, but we still don't have enough information. So just know that 7 is on here and 7 is on this diagonal line, which could be anywhere. So that's all we know. Oh, another thing, 6, 7, right? So now we're gonna go to this guy, which is 7G. So there's gotta be a horizontal line from G that intersects with point 7, which is kind of interesting. So 7 must be on this horizontal line somewhere. So actually, without even locating this diagonal line, just by the fact that 7 is on this horizontal and the vertical, makes us conclude actually 6 and 7 are identical points, which means actually this member 6, 7, if you connect those 2 points here, you end up with 0 force. So you actually do have 0 force in this vertical member, which kind of makes sense. You have this downward force and the compression is taken care of by these 2. So anyway, so that actually helps us eliminate these. And 7, it's also on this line somewhere. So now it's gonna actually kind of force us to conclude that this diagonal, which passed through 7 and 8, now has to, because we know where point 7 is, so we know this diagonal is going to pass through point 7. Point 8 is going to be somewhere on this diagonal, but we knew also point 8 was going to be on this horizontal somewhere. So the only possibility is intersection between these 2. And that point is going to be point 8. Moving forward, I guess I'm gonna go here next. So 7 is here. Unfortunately, so what we can tell is that because the geometry of the truss is symmetrical, you can pretty much predict that your force diagram will end up being symmetrical too. So it's gotta look like this somehow. But unfortunately, you kind of have to go through everything because we want to locate all the points. That you kind of have to look at everything. But let's just but your diagram is gonna end up looking like this, and that's a fair assumption. If the geometry of the truss is symmetrical, your diagram should always, I mean, if the geometry and the force loading is symmetrical, your diagram should end up looking symmetrical too. So I'm just gonna, yeah.
So on the left is the triangular sort of piece, and then on the right is the roller. Would that change the force diagram?
No, unless you have, in this case, everything is symmetrical. And the reason why one is roller and one is pin is that if you imagine a movement between these 2 support, right? If you had pin and pin, the structure is going to do that, right? But and that's why you want to have pin and roller, because you know, if there was some kind of a movement, the roller can sort of absorb that, and there's only horizontal reaction would be on this side. And it's also, if it's pin joint on both sides, there can be horizontal reactions on both ends, which actually makes this whole system indeterminate, meaning that we can't really calculate the reactions at each point. So typically, like all of the problems that we are going to look at will have pin joint and roller joint at each end. I mean, it's going to be a different story if the loading pattern is different, like if you had a bigger force here, or like if you had some sort of a diagonal force, then you can't make that assumption. But right now, because everything is completely symmetrical, I'm kind of making that assumption. But anyway, so looking at G7 is horizontal force, so but we haven't really located 7 yet, right? But we know, actually we did, right? So 7 is here too, so G7 is here. 7, 8 we've located it already, and 8, 9 will be on this vertical. And so if I were to do it, I could pretend that I don't know, and 9 would be somewhere on here. But 9, there's also 9G, which sandwiches this horizontal one, so there's got to be a horizontal line connecting 9 to G. So we can actually conclude that 9 is here as well. G7. Right. So I guess it's gotta be pretty self-explanatory, but just for the sake of video recording, I'm gonna keep going, but if you wanna leave, you can leave. But I would say, so I'll be talking to no one, but moving to the next node, zone 8, zone 9, D, E, and 10 is here. So looking at the vertical one first, between 9 and 8, there's a vertical force, so it's already mapped here as 9, 8. 8D is already mapped here as horizontal, 8D. DE is already mapped, and the new one here is E10. So E10, 10 would be on this horizontal line somewhere. And there's also 9, 10, 10, 9, which is this diagonal force, which starts from 9. So the 10 automatically must be at the intersection point between this diagonal and horizontal. So moving forward, E10 is already mapped here, so we're gonna move to the next node. Ten, 11, 9, and G. G9 is already mapped horizontally. 9, 10 is already mapped. 10, 11 is not there, so it's got to be some sort of this vertical force starting from 10. 11 would be mapped along that vertical line somewhere. But we also know from this 11G is a horizontal force that's starting from 11 ending at G. So basically 11 must be at the intersection of these two lines, which means 11 is actually identical to point 2. Right, so now we're gonna move on to the next point. So 10, 11 is already mapped as the vertical force, 1110. 10E is already here. EF is the vertical force that's already mapped. F12 is not mapped yet.
And also, I really appreciate your requirement.
Alright, so moving to the next node. So F12 is the new one. So there's a horizontal line somewhere here, and the 12 is going to be on this line. But just looking at the symmetrical nature of this diagram and the fact that A and 1 was here, it's not hard to assume that F and 12 is identical, but let's just keep going. 12, 11 is here, is diagonal. Point 11 is already identified, and the fact that the intersection between this and this is 12 makes us determine that actually F is identical to 12. Moving on to 1110, which is here. 10E is already mapped. Yeah, so we've already looked at that. Moving on to the last point. G is here. 11 is here. 12 is here. And F is out here. So now FG is already mapped. G11 is already mapped. 1112 is already mapped here. 12F is also mapped here. FG is mapped. Moving to the last point, 12 and F, that's already mapped, and 12F is 0. And that concludes the drawing of the force diagram, and we're gonna look at the in the next class we're gonna cover how to identify the forces in each member using the force diagram.